Okay, so welcome to this video where we're going to be talking about an adiabatic flame with a steady state system. So we're going to go ahead and write both of those keywords down because those are going to be the two keywords throughout this entire this entire video. So um, adiabatic flame system with steady state. So for both of these, so adiabatic means there's going to be no temperature leaving the system, and there's going to be no heat being put into the system throughout the duration of its course. And steady state means there's going to be no mass gain or loss, more specifically mass loss throughout this system. So to explain it further, so let's say we have a system, so it could be an oven, a torch, literally anything that could cause a flame. Um, so we're going to be putting fuel in, and more specifically, we're going to be putting a mixture of methane, ethane, and propane as the fuel. And then we're obviously going to have, if I can spell it right, air going into the system, and then obviously going out, we are going to get the resultant flame out of that. So, as said before, this system is going to be completely perfect in the fact that no energy is going to be lost out of the system, or heat rather, and no heat's going to be being put into the system, and we're not going to lose any mass out of this. Now, in terms of what this means for an energy mass balance or just an energy balance, excuse me. Typically, you would have like the change in mass is equal to like the change in enthalpy and everything like that. But since the change in mass is negligible, that means our entire left side of the equation is going to be completely zero because there's going to be no change on that side. And then on the right side, it's just going to be equal to our enthalpy in minus our enthalpy out of the entire system is going to be equal to zero. So we can go ahead and say that our enthalpy in is equal to our enthalpy out, and that's going to help us substantially in the course of this. So we can go ahead and rewrite this as our. So actually, let me go ahead and write this here for good measure. So our enthalpy in is equal to our enthalpy out. So our heat of formation let me take a step back here. So this starting temperature right here is going to be at 298 Kelvin, and we want to see what the final temperature is going to be of that flame with a certain mixture and the air that we have going in, because we'll see later that we're not just dealing, obviously the air that we have is not 100% oxygen. It's a mixture of a bunch of things. We'll come to that later. So we start at 298 Kelvin, and the result, we want to see what the resulting temperature of this flame is. So we can call that T final. So our heat of formation, let me put this in order. The heat of formation at 298 Kelvin is going to be equal to the heat of formation at that certain temperature minus an integration of from 298 Kelvin to the temperature of the specific heat of the gas, because we're going to go ahead and say that's an ideal gas because we can use those properties that we have with our CHE tools in Python. And then this is with respect to time, so we'll put that as a little t, or I guess that's T final, and we'll keep that as a little t just for continuity's sake. So this integration of this specific heat capacity, there's a equation in ChemCAD. It's equation 107, and it is used for the change almost of specific heat for different gases with different constants, and we have those constants. So yeah, if we go ahead and look here, this is equation 107 right here. So this is the very simple. I mean, it's the equation that we're going to use, and we have to integrate this to make it part of our equation because it has to be with respect to time because it's going to be changing. And just to make things a lot simpler, because that would be a little tough to integrate, we're going to be using Wolfram Alpha to integrate those two parts because, as you can see, this A, that's easy to integrate. And then this B times this, that's just a constant, so we can keep that out. So we just need to integrate this part. Oh, we'll highlight. It won't highlight, but we just need to integrate this part right here and this part right here. The D and the B, they are not negligible in the integration. They just don't factor into it, just laws of integration. So if you use Wolfram Alpha, I already typed it out just to save time. So this is part one. So it's, if we look back, I could probably put it side by side. Okay, we're not. So it's C over T over sine H, so the hyperbolic sine of C over T squared, and that is what we have. Let me put this back up here. And that is what we have in here. So C over T over sine H of C over T and then squared with respect to time. So we can go ahead and compute that, wait for it to load. And this is going to be the resultant of that. So our change in the temperature is going to be equal to the constant C, times the hyperbolic cotangent of C over T plus a constant, but we don't need to worry about that constant because it's not going to affect our calculations too much. And then if we look back, the second equation of that is the same exact thing, except it's cosine H, and then just with the E instead of a C. So we can go ahead and change that. So change that to an E. Same thing here. And then change this to cosine H, and then compute that. Wait for it to load. And we can see it's negative E, which is, it's taking in this, it's the same kind of thing. Tangent, the hyperbolic tangent of E over T plus a constant. So from there, let me go back up to here. So from there, we know the integration part, so we can compute that. Our only thing now is we need to have the specific moles of each of them put in because we have a certain mixture of everything, so we need to know everything. So let's go ahead and write this down. So we have methane, which is CH4, ethane, which is C2H6, and then we have propane, which is C3H8. So when you run a combustion reaction, you combust it with oxygen, but like I said, I would explain it later, we are doing this within a system because air obviously isn't 100% oxygen, or else it would combust a lot more violently than it does in real life. So we have a 79 to 21 mixture of oxygen and nitrogen. So we're going to be combusting it with nitrogen as well. So let me write this up here. So 79 nitrogen for 21 oxygen. So if we do that for all of these, and then we can balance the equation out and see kind of the mole ratios of each individual part. So this reaction, obviously, basic combustion reaction, so we'll get carbon dioxide as a product. Actually, I need to make this smaller so I have room to right. So we have carbon dioxide as a product, and then we also get water, and we get the nitrogen back because the nitrogen is inert in this case and does not react with the combustion, but it does have a very important effect on temperature because if we just had 100% oxygen, all of that energy would be used to combust the oxygen, resulting in a higher heat of the flame. But instead, since that nitrogen is inert in this specific reaction, a lot of the temperature is going to be used to heat up that nitrogen um, throughout the duration of the reaction. So we're gonna result in a lower temperature of a flame at the end than we would if we had 100% oxygen. Um, so yeah, now we can just kind of balance these out. So we can go ahead and start with the ethane. So if we just have not ethane, methane. If we just have one methane, so we have one carbon there. So that means we have to have one here. So then we have to have 4 hydrogens. So this needs to be a 2. That means we have 2 oxygens over here, 2 more oxygens over there. So we need to have 2 of these, which means we have 2 nitrogens as well. And then we can just keep doing this along. So this is 2, 3. So that's 1, 6 hydrogens. So that means we have to have 3 of these. I mess up here. No. Yeah. So 3 of those, 2 of those. So 4, 7. Okay, yeah. So we have to have, yeah. So 7 halves oxygen. Yeah. Okay. I was getting tripped up there. So it means we have 7 halves nitrogen, 7 halves nitrogen on that side, and then we need to have 3 there, 8 oxygen, or 8 hydrogens, so we need to have 4 there, so 4 oxygens, and then we have 6 oxygens, so we have 10, so we need 5 here, so then we're going to have 5 there and 5 there. And then to kind of incorporate the 79 to 21 mixture, we are going to multiply all of these nitrogens by this coefficient. So it's going to be 79 over 21 times this 2 right here. And we're just going to do that for every single nitrogen that we have. Every coefficient that we have is going to be multiplied by 79 over 21 to kind of give us that even molar ratio that we see with the oxygen. So from there, we have pretty much everything we need to kind of code this out. So now we can go ahead, because now if we do the heat of formation, everything like that, we know all the moles, everything like that. We have the integration from Wolfram Alpha. So we can go ahead and jump into the code. Okay, so now we have moved on to the coding part of this. So I just went ahead and I imported the necessary things. So the first thing up here is just importing the our like chemistry database that we have right here that has like all the properties of everything we have. So we have like ethane right here, and it has all the data that we need for like the coefficients that we saw in the integration part, and then we imported numerical Python for math purposes. We also imported scientific Python .optimize and the root part of that, so we can solve for our root at the end, which is going to be the final temperature. And then again, we just have to import the right database within the CHE part. So what we can go ahead and start off by doing is importing all of that data from the CHE tools. So we're going to do P equals CHE dot the properties, and then we are going to import each individual one. So we have methane to start off, and then ethane, and then we have N, propane, excuse me, and then the next one we have is our oxygen, and then the nitrogen. Oh, if I spelled it right, nitrogen, and then all of the byproducts. So then we have CO2. Yeah, I believe it's CO2. We'll find out if it's not. And then we have water. So we can go ahead and import those. Attribute its props. Okay, we'll try that again. And CO2 no available data. So we'll see what it is. Okay, I was wrong. Carbon dioxide, that's what it is. So shift into that, and hopefully it works this time. H2O. Or is it just, it's just water. Okay. Okay, so now, after doing all that, we can go ahead and input the integration that we had from the Wolfram Alpha and the ChemCAD 107 equation. So we're going to go ahead and make that a function. So we're going to define it as, so it's the delta, so change in the, not specific heat, it's sensible heat, that's what it is. So we'll do that of an ideal gas, and then we input the final temperature, and then we want to return the entire equation. So to start off, so it's yeah, it's from P. So the specific heat of an ideal gas, and then A, and then that was times temperature after the integration, and then it was plus the specific heat, CPIG, the B coefficient, and then that was multiplied by cotangent, but numerical Python doesn't have a cotangent function, so we can just go ahead and do 1 over tangent h. So that was multiplied by, it was c times cotangent, so it's going to be c over tangent. So times p dot cp igc divided by np dot tangent h of the same thing, so p dot cp igc over the temperature. And I'm just going to put these in more parentheses just to make sure it's right. That. And then this was minus the D coefficient times the same thing. So CPIGD times, and then this one was just straight up tangent, so I already put multiplication, so MP dot tangent H of P dot CP IG, and then the E coefficient divided by temperature. Yes. Make sure that's right. Yeah. And then with the properties, it is actually in kilomoles, I believe, or it's not in just moles. So we have to divide it by 1,000 to get it in moles, which is what we're dealing with in this case. So then we can go ahead and make sure it's right. Yep. And then we want to go ahead and define another function, which will just be the heat of the ideal gas. So we'll call it HIG. And then we want to pass in two variables, so the number of moles and then the temperature. And that. And then we are going to return the dot product, passing in the number of moles, and then the properties of the heat of formation for an ideal gas. And then we're going to add another dot product, dot, and then number of moles, and then the second equation is going to be the one we just did above. So DHSIG of the final temperature minus the same thing. So of the starting temperature, which is 298 Kelvin. And that gives us kind of the extra range in between after the first equation, which will just help us further solve the final temperature of that. And then now we can actually insert the original formula, and we can put in the number of moles of every single of carbon, hydrogen, and then from there we can say how many moles of water, how many moles of everything else we have. So first off, from the original equation, we need to make an array. So everything that we calculated on the iPad, so we can say that the we'll say fuel, for fuel formula, is equal to an array. And then we originally had for methane, so we had 1 carbon and then 4 hydrogens, because this is for just the number of moles of carbon and hydrogen. So we have 1, 4, and then we had for ethane 2, 6, battery close off, and then we have 3, 8. And then from there we have, as I mentioned before, we have a specific ratio of each. It's not just 1 to 1 to 1. So we can say that we'll say the number of moles of fuel is equal to P dot array, and then that, and then we have a 10 to 1.5 to 1 ratio of all of those. And then so then now we need to do a matrix multiplication of, actually let me change this because that's not going to be we'll just put an R there for fuel, for ratio I mean. So then now we can say that this is equal to matrix multiplied by fuel F and then that should, yes, and then that lines up with that. Okay, so yeah, so now we have the correct like ratio almost of the amount of methane, ethane, and propane that we have in there. So now what we can do is, oh wait, no, we don't need to do that. We need to say that the number of moles of carbon and the number of moles of hydrogen is equal to this. And then now we can say that the number of moles of carbon dioxide is equal to the number of moles of carbon. Nope, not moles. Is equal to the number of moles of carbon. The number of moles of carbon. There we go. And then from there we can do that's the number of moles of water excuse me, is equal to the number of moles of hydrogen and then divided by 2 because there's 2 hydrogens per water. So I'll do that. And then now the number of moles of oxygen, yeah, O2, is equal to the number of moles of carbon dioxide no. I think it's the number of moles of carbon. Yeah, number of moles of carbon plus the number of moles of water divided by 2. And then the number of moles of nitrogen is equal to that ratio, so 79 over 21 times the number of moles of carbon dioxide. No. It's equal, oh, I know, of O2. My brain is not working today. So then now we should have that. Array takes. I do not need to have an array right here. Hopefully it should work. Yep. Okay, so now we can do something called concatenate for our intake and our outtake of our products. So we'll start with intake, so we can just call it intake is equal to numerical Python dot concatenate, and then at first we pass in the starting ratio of fuel, and then we will next add an array. So array of, and then we have our starting one. So we have the number of moles of O2, and then the number of moles of nitrogen, and then none of the either products, so no carbon dioxide or water yet, and then, yeah, that's right. Wait, yeah, okay. And then our products, so we can just call it prod, is the same thing, so np dot concatenate, and then we have no fuel at this point, so we're just going to do np dot zeros like, and then nr fuel. Yeah. And then we can do the same thing, so np dot array. We have no water left, or no oxygen left, and then we have the number of moles of N2, the number of moles of carbon dioxide first, so CO2, and then the number of moles of water. Excuse me. There we go. Okay, so then now we can do our energy balance equation where we have everything set up for that part finally. So now we can just define the energy balance. So I'm just going to call it EB. And then we want to pass in our temperature, our unknown temperature again. And then we are going to want to return the second function that we did, so HIG, and then the first parameter is going to be intake, because that's going to be the number of moles of the intake, and then we want that at the starting temperature, which is 298, and then we are just going to subtract HIG again, and this is going to be for the products, and then temperature, and then next, then we can do the root solver to see what the final temperature is going to be for that. So roots, and then we can just do EB, and then pass in 298. And that should give us, yep, the solution converged, and it'll, it says that the final temperature will be around 2400 Kelvin for the final temperature. So that was this video about an adiabatic flame with a steady state, so no mass loss and no heat lost or gained, with not just oxygen, with nitrogen thrown in there as well, and with multiple different fuel sources and different ratios. So yeah.